Recording. Just confirm if you can see my shared screen.
Yes, sir, I can.
All right. I just from your free body diagram, I felt like I needed to explain something here.
Okay, sir.
Right now, in drawing your free body diagram for any problems based on dynamics, né?
Mm.
Especially the ones where the object is moving on an inclined plane. As far as showing your forces, right? Now, if you read here, they said a motor car of 1,200 kilograms is at rest at the top of a 15 meters frictionless slope of 28 degrees to the ground. Right, so you have a slope. Right, the slope is at an angle of 28 degrees to the ground. Right, so we're going to take this as the ground. That's our slope, hence the 28 degrees. Now the object is at the top of the slope. Né? Now, before any kind of motion taking place here, you need to consider the fact that you already have these following forces at play here. Right, so when this is still at rest, right, you have these forces, right? You already know that you are going to have um, the weight component perpendicular, the weight component perpendicular to the plane, right? That is the weight component perpendicular to the plane. That's mg cos theta, right? So before this even starts moving, right, these are the forces that this object is subjected to, right? And then here you have Fg parallel. In fact, here, let me say Fg perpendicular, right? You have this here, and then you also have the normal force. Let's make this one white. Right. So Fn for normal force. Right. Now, when the object is still at rest, these are the forces that are acting on this object. Right. Before it even starts moving. Right. So that is to say that I saw your weight component parallel to the plane. It was heading in this direction. Right.
Yes, sir.
Right. Which is incorrect. This is always acting in that direction, and this one is always acting in this direction. The normal force always heading in that direction. So these three forces are always in this direction, always, right? And they do not change under any circumstances, whether this is moving down the slope or moving up the slope, whether a force is applied or not. These forces are always in this direction,
Okay,
right?
sir.
Because these are the forces that this object, right, is subjected to even before the object is in motion. Nah.
Yes, sir.
Now, going back to the statement, they said that this slope is 15 meters long. It is also frictionless. So if it is frictionless, it means there is no frictional force here, or the frictional force is so small that we take it as being negligible. Right. So if the slope is frictionless, it means essentially there's no friction. Right. Now they say when the brakes of the motor car are released, it slides down the hill on its own, and at the bottom is immediately and at the bottom it immediately moves on a horizontal road until it comes to a standstill after 20 meters. Right. So this object is being kept at the top of the hill because brakes are being applied. So as soon as those brakes are released, this then starts moving down the incline on its own, right? After which, when it gets to the bottom of the incline, it then comes onto a horizontal road, right? And the object, which is the motor car, so the motor car right, gets on the horizontal road, and then after 20 meters, it comes to a stop. All right. So as far as other forces that this object is being subjected to when the brakes are released, which are those forces? There are absolutely none. Why? There is no force that is applied here for this to move down the incline. So it means that if it moves down the incline on its own, it means it moves down the incline because of this weight component that is in the same direction, right, as the work being done, or that is in the same plane or same, what is this, same set of axes where the work is being done. So the work is being done along the x-axis. The only force that contributes to this going down the incline that is parallel to the x-axis is this one. So which means this goes down the incline because of this force, but only once the brakes are released. Are we still together here?
Yes, sir.
Right. So there's no frictional force. Why? Because they said the surface is frictionless. So there is no force opposing the motion due to friction. Right. Also, there is no force applied here. Right. We were told, or from the statement, nothing suggests that there is a force being applied. They just said the brakes are released and it slides down the hill on its own. If it's sliding down the hill on its own, it's because of this weight component that is in the same axis as the work being done. Right. So essentially, this here is your your free body diagram. Right. So these are the only forces involved. Now, what do the forces tell us? So as far as the direction of acceleration, right, acceleration is in this direction. So that's your acceleration. So acceleration is in the same direction as this weight component. Now, what does that tell us regarding F net? Right. Remember that with F net, right? So F net being the vector sum of forces, right, acting in or on this object along the axis where the work is being done. Right. You look at the forces that are going in the same direction as acceleration. Those forces you take as positive. The ones going against acceleration or the direction thereof you take as negative. Right. So keeping that in mind, also seeing that this is the only force here to consider because that's the only force um, that this object is subjected to along the axis where the work is being done. You then look at your force, right, and look at or compare the directions of your force and the direction of acceleration. Obviously, it's going in the same direction as acceleration, so you take it as positive. So this would be positive Fg parallel. It means that the next force or the resultant force or the vector sum of forces acting on this object, right, they are equivalent to Fg parallel. I will see together.
Yes, sir.
When you break down your free body diagram, these are the steps that you take, right? You look at the forces that the object is being subjected to before it even moves, right? And those forces are the normal force and the two weight components, right? And then you look at if the object is moving, the direction it is moving in, right? And establish if there's a force being applied or not. Do you have friction? Is the slope frictionless or not? Then you look at the direction of acceleration, right? If your object is accelerating, it will be in the same direction as the direction of motion. If the object is decelerating, then the acceleration will be in the opposite direction of the direction of motion, right? That is how you break down your free body diagram. After having established that, you will then be able to establish what the vector sum of forces is equal to, right? From there, you then look at what else you've been given and what it is that they're looking for. Now, we are told that the slope is 15 meters long. So the distance, right, of the slope is 15 meters long. The slope angle is 28 degrees. And then we are also told that the horizontal road is 20 meters essentially, right? Because the object takes 20 meters to come to a standstill. Right? Now, another thing that we do have is the initial velocity. Right? The initial velocity, which is the velocity at the top of the hill. We know that this was at rest. Because this was at rest, it means the initial velocity is what? 0. 0 meters per second. Are we agreed there?
Yes, sir.
And then you have the mass of the motor car. It's 1,200 kgs. Right? What else? What else? What else? Yeah, that's pretty much it as far as the data we've been given. Maybe let me write here. This is the given data. Right, now let's look at 4.1. So we're going to do all of them. Right, 4.1, calculate the potential energy of the motor car at the top of the slope. So they want us to calculate the potential energy of the motor car at the top of the slope. All right, we know EP in general is equal to mgh. What determines the magnitude of EP is essentially h. The mass remains constant, g is always constant. So this is the only quantity that can change. Right. So in order to calculate EP, right, at the top of the hill, you need to establish what this h is equal to, which is this height here. Right. Because remember that the h for potential energy is always referenced from the ground. Right. So we have to calculate this h. Are we in agreement there?
Yes, sir.
Right. So we need to calculate this h. And then if you look here, right, so this is the h we need to calculate. Right, it's the dotted one. Now, if you look at having to calculate this h, you essentially have a right angle triangle, right? So to calculate this h, you have this angle and you have this side, right? And the side, the side that represents h is essentially opposite the angle. The side we have is essentially the hypotenuse of this right angle triangle. So it means that in terms of the trig ratio that you can use here, it is sine theta, right? Remember sine theta. So sine 20 degrees, theta is 20 degrees. Sine theta is equal to the opposite side over the hypotenuse. The opposite side is the h. The hypotenuse, right? The hypotenuse is the distance of the slope, which we are given as 15 meters, meaning that the h is equal to 15 sine 28. Right. So having established what this h is equal to, it means now you can get your EP. Are we still together?
Yes, sir.
Right. So EP, we can write EP at the top to give it context, is equal to M times G times H at the top. The mass is 1,200. G for science is 9,8. H we have just established is equal to 15. So it's 15 sine 28 degrees. And what is this equal to? So it's 1,200 times 9,8 times 15 sine 28. So I'm getting 82814,784. And then this is in joules. Are you getting the same thing?
Yes, sir.
Right. That's 4.1. Easy, straightforward. So you got 4.1 correctly because it didn't necessarily need acquire or didn't require you to use FG parallel. So even though your FG was incorrect, it didn't really have an influence on having to calculate EP at the top. Right, so that is why 4.1 was correct on your calculation. All right, 4.2. calculates the kinetic energy of the motor car when it has moved 7 meters down the slope. Right? Just take this away. Right. So they want us to calculate the kinetic energy of the motor car when it has moved 7 meters down the slope. Right. So brakes are released. This starts moving down the incline. Now they want us to calculate the kinetic energy that has been accumulated from when the brakes are released to to the car having traveled 7 meters down the incline. Right. Now there's many ways in which you can do that. Right. One of which, probably the simplest one, is having to use the what is this? The conservation of energy equation. Right. That equation is the work done. So here, because the object is accelerating, that is why we make use of this. So total work done plus EK at the first point plus EP at the first point is equal to EK at the second point plus EP at the second point plus the work done to overcome friction. Right, the work done to overcome frictional resistance. Right, now here, remember that there is no force being applied here in order for the object to move down the incline. Right, there is no FT. There's no total force being applied. Right, Lara, Lara.
Sorry, sorry, sir.
Yes.
I want to ask, you said we use this formula because of what?
You mean this one?
This, yeah. We use it because of what?
Right. So we are able to use this. You can use this formula under any circumstances, right? If you have to, say, calculate anything pertaining to energy or quantities that we are able to get based on energy, right? For EP, that's H. For EK, that's velocity, right? But using this here, right, we use that because, or we express it like this, including the total work done, right? Because what is this? Because the object is accelerating, right? We
Mm.
only are able to use this if the object is accelerating. But if the object is decelerating, right? Remember, when the object is accelerating, we consider the total force being applied, if there is any. When the object is decelerating, right, we use instead the braking force, right?
Mm.
The work done due to a force being applied is, remember that it'll be ft times the distance traveled. And then if the the object is braking, right, we instead consider the work done due to the braking force, or the work done by the braking force, which will then be equal to fb times s. Right, now I saw that I gave you the wrong what is this, the wrong, the what is this, the formula I gave you when the object is decelerating, right? It doesn't give context. So in a way, it is incorrect. What I should have told you, or what I should have given you, is that when the object is decelerating, then this is what you will have instead. So EK2 plus EP2 plus the work done by the braking force, or the work done due to braking, plus the work done to overcome friction. Right. The reason why this is on this side is because when the object is braking, right, it is already in motion. So meaning that the braking takes place on the two parts of the equation, because the object is already in motion. Hence, this cannot be on this side contextually. Do you get what I mean here?
Yes, sir.
right? So this gives context, right? Whereas the one I gave you initially doesn't really give context, right? Which I understand if people were confused by it, right? This is the equation, or this is the version of the equation that is correct, because this one is based on context, or on the context that when the object um, starts decelerating, it is because, or it starts decelerating while it is already in motion. Hence, this work done only takes place, right, after, right, after the object had already been moving, right. Whereas this side, this is when the object, um, say, moves from the initial point, right. Whereas this one is when we consider, right, after the work being done, or after, yes, after work has been, or after work has already taken place, right. Now, like I said, this one we use, or this version is used when the object is accelerating, because for the most part, especially if, say, the object is moving up the incline, right, a force has to be applied for the object to move up the incline. Hence, initially there's going to be some work done for the object to even start moving up the incline, right. That is why contextually this one must be on the left hand side, right. Why? Because initially, right, if the object is, say, moving up the incline, work done, so some work has to be done for the object to then start moving up the incline, right. Now here the object is accelerating, but there is no, did I do? There is no force being applied for the object to move down the incline, which means this here is equal to zero. Also, the slope is frictionless, so there is no work done to overcome friction, which means essentially you have ek1. Okay, in fact, let me do this, right. So this and that is gone, and then also initially the object is at rest, meaning that the initial velocity is equal to zero. So which means the kinetic energy initially is equal to zero. So we also do not have that, right? And then because this is at a height h from the ground, there is some potential, right? And then it moves 7 meters from the top of the hill, right? So say to that point, right? And at that point, the object has accumulated some kinetic energy, which is the one we need to calculate. And then also at this point, this is still at a height h from the ground, meaning that you have some potential as well. So which means this will now be EP is equal to EK2 plus EP2. Are we still together?
Yes, sir.
Right. Now remember what it is that we're looking for. We're looking for the kinetic energy, right? That's the second point. The second point of which is 7 meters away from the starting point, which is this one. So from here to 7 meters down the incline, right? We're looking for the kinetic energy, say at this point, right? Now we've already calculated EP1. Remember, EP1 is the positional energy at the top, which we've already calculated, right? Now we need to determine the potential energy, right? After having um, gone a distance of 7 meters down the incline, right? We already know what determines a potential energy, right? It is the height h. So which means we need to get, say, we need to establish what this H is equal to. All right, let's call this H2. All right, we need to establish what that H is equal to so that we are able to calculate the EP at 2. All right, so EP at point 2 is equal to M times G times H2. So once you have H2, you would then have EP2. Right? Now, the question is, just like how we calculated this H, we are going to do the same with this one. Because if you look here, again, you have somewhat of a right angle triangle. The angle of incline is still 20 degrees. Now, what is this distance equal to now? Right, we are still going to use sine 28 is equal to, the side we're looking for is opposite the H. So this will be H2 divided by the hypotenuse. What is the hypotenuse equal to here? Remember,
8.
yes, because this is 15. 15 minus the 7 leaves us with 8. Right, so divided by 8, meaning that H2 is 8 sine 28. Right, and that essentially gives us the height H. I mean, that give us H2. Having gotten H2, it means we can get EP2. So now, going back to our equation, right, we are looking for EK2. So we can say here EP1 we know is equal to 82814,784 is equal to EK2, which is what you're looking for. Plus, we know that this is equal to MgH2, which is going to be, the mass is, what is this, 1000. 1200. G is 9.8. And then H2 we established is equal to 8 sine 28. Right? And then this will be 82814,784 is equal to EK2 plus, so let's calculate, this is 1200 times 9.8 times 8 sine 28. So this is 44167,8885. And then to get EK2, you make EK2 the subject, hence you transpose this to the other side, hence you will have 82814,784, then that becomes negative 44167,885. And this should give us our EK2. So 82814,784 minus 44167,885. And then this gives us 38646,899 joules. Are we getting the same thing here? Hello.
Yes, sir.
All right. So that's 4.2. That is why it is important that you understand um, how to express the conservation of energy mathematically. Right? It's the object is accelerating or the object is decelerating. Right? It's very important you understand how to use the conservation of energy or how to express conservation of energy mathematically. Comes in handy for such cases. All right. Right. Can we move on to 4.3?
We can, sir.
All right. Right. 4.3. The time it took the motor car to travel on a horizontal road until standstill. So now they want us to calculate the time it took for the motor car to come to a standstill from the time the motor car came into the horizontal road, right, to when it had traveled 20 meters, essentially. Right, that is what they want us to calculate. The time it took for the car to come to a standstill from when it comes, right, when it comes onto the horizontal road, right, to when it comes to a standstill or after having traveled 20 meters, right? Now, as far as having using time, it obviously means, or us having to calculate time, it means we are going to have to make use of an equation of motion, right? What are they called again? Another term for equation of, oh yes, it is equation of motion. So either equation of motion or kinematic equation, right? Kinematic equation, equation of motion, that's one and the same thing, right? Us having to calculate time means that we have to make use of an equation of motion, right? Now, we have the distance as per the horizontal road, that's 20 meters, right? We know the final velocity here is going to be equal to 0 meters per second, right? And then we do not have at the moment the initial velocity, right, where the horizontal road begins. Now that it is important to take note that the initial velocity on the horizontal road is essentially equal to the final velocity on or at the bottom of the slope. Do you see what I mean here? The final velocity on the at the bottom of the slope is equal to the initial velocity, right, at the beginning of the horizontal road. Are we in agreement there?
Yes, sir.
Right. So it means in order to get the initial velocity on the horizontal road, we need to calculate the velocity or final velocity or the velocity at the bottom of the slope. Right. Now you can go back to using this. Right. In
Mm.
fact, let's what is this? Let's use both. So you have EK. Oh man, you have this is 4.3. Right. WT plus EK1 plus EP1 is equal to EK2 plus EP2 plus work done to overcome frictional resistance. Right, we know this and that are not there. Kinetic energy at the top is equal to 0. Kinetic energy at the bottom, we are going to have some kinetic energy at the bottom because by the time the motor car gets to the bottom, it has already accumulated, right? Essentially, its maximum kinetic energy. The potential energy at the bottom, what is it equal to? So the potential energy here, what is that equal to? Audi.
Thomas is the 82,814.
The potential energy here at the bottom, what is that equal to?
Mm. So isn't it the same as when it's at the top?
Can't be. Remember, potential energy is equal to mgh. This is the determining factor, h. So is there enough height at the bottom of the slope for
Oh
there to
no,
be considerable amount of potential energy?
no, sir. So it's
Exactly.
zero.
So it's 0. Yes. So the
Oh,
potential energy at the bottom is 0. So essentially, EP1 is equal to EK2. So essentially, the potential energy at the top is equal to the kinetic energy at the bottom. Why is that? Because there is no friction. Because there is no friction, and also because there is no force being applied. That is why the potential energy at the top is equal to the kinetic energy at the bottom. All right, so that is to say that thing that we're looking for. So remember EK2, this is EP1 is equal to EK2 will be half times M times final, call this V2 squared. Right, and this is what we are looking for, V2. Right, and then here EP1 we already know is equal to that 82814,784 is equal to half times the mass, which is 1200 times V2 squared. Right, half of 1200 is what? 600. So this will be 82814,784 is equal to 600 V2 squared. All right, you always divide both sides by the 600. All right, that cancels, and you're on the left hand side, you're left with V2 squared is equal to, and then this you can take down exactly as it is, or you can calculate it, up to you. All right, and then to calculate V2, you have to use the square roots on both sides. On the left hand side, the square root eliminates the square. On the right hand side, we have the square root of this. Right, of which we get the square root of 82814,784 divided by 600, which is 11,748 meters per second. Are we in agreement here? Hello?
Yes, sir, I got the same answer.
Right. Now, here it is important to note that when there is no force being applied, right, for the object to start moving, and also the surface is frictionless. So if the surface is frictionless, so if there's no friction and there is no force being applied, right, in terms of
Mm.
the potential energy at the top will be equal to the kinetic energy at the bottom, right? So instead of doing all this to calculate the final velocity or the velocity of the motor car at the bottom, right, you can simply use this instead. So this equation I'm about to write down, you only get to use if there is no force being applied and the slope is frictionless. Right, that is right. Velocity at the bottom of the slope is equal to the square root of 2 times g times h at the top. Right, take note of this. Right, instead of doing all this, you can simply use that. This equation is only relevant if there is no force being applied and
And there's
so
friction.
for the surface is frictionless. Then the velocity at the bottom will be equivalent to this here. And then from here, you can say square root of the square root of 2 times G times H top. H top is equal to, remember, H top is equal to 15 sine 28. So you write here 15 sine 28. And then you will get something equivalent to what we got at the top. So square root of 2 times 9,8 times 15 sine 28. That's equal to 11,748 meters per second. Right. In fact, it is.
Wow, the same.
You see?
Yeah.
But you should take note that only when there is no force applied, and also if the surface is frictionless, only then can you use this formula to calculate the velocity at the bottom of the slope. Right? But you see that if you take that into account, it's much easier. Right? So using this is much easier, much quicker than having to use this here. Right? That is why this equation is very important. Let me write here. Alternative. Right, so this is the alternative answer. I don't know what happened now. This is freezing. Okay, just give me a moment. This has decided to freeze on me now. But do you understand what I mean by why this equation is important to us, right? But also understanding how and when to use it.
Yes, sir.
All right. There we go. Right. Move this here, and then write this as an alternative. Right. So alternatively, you can calculate the velocity at the bottom simply using that. Right. Now, if the velocity at the bottom is equal to this, it means the initial velocity on the horizontal road is equal to the 11,784 meters per second. Now we have the initial velocity at on the horizontal road, and we also have the final velocity on the horizontal road. We also have s, the distance moved by the car before it comes to a standstill. Right. So now you have to think about the what is this the equation of motion that is relevant or that is convenient for us to use, bearing in mind that we are looking for time. Now, because we have the distance, we have both velocities, so we have both v and u divided by 2, and we are looking for time. So this one is the most convenient for us to use. Why? We have s, we essentially have both of these, and we're looking for t. And then solving for t or making t the subject of the formula, then this will be 2 times s divided by u. let me write it v plus u, right? So this will be 2 times the s is 20 divided by final velocity is 0, initial velocity is 11,748, and this here will give us our time in seconds, right? So this is, numerator is 2 times 20, denominator is 0 plus 11,748. So I'm getting here 3,405 seconds. Getting the same thing?
Yes, sir.
Right. So you see how everything goes back to how you drew your free body diagram. If you draw your free body diagram correctly, it will tell you everything you need to know, right, regarding everything um, that they've asked you to calculate. If you draw this correctly, you will be able to answer these correctly as well. The free body diagram never lies, right? It will always tell you exactly what you need to know to solve whatever question is based, right, on your free body diagram. Any questions?
I don't have questions concerning this thing.
All right. Any other questions concerning dynamics?
Sir, um, I do not understand when they say that the slope is in percentage. Like, I don't understand that concept because I calculated it as the if they say 80% of the slope, then I would say 80% of 90 degrees, and I get very strange answers. So I don't know how to calculate that.
So the slope is the same as the incline, right?
Oh,
When they've given you the percentage of the slope, um, essentially that's like them giving you the what is this thing? Uh, 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 um, the gradient, right? Remember, gradient and slope is the same thing. So if say they say that the the slope is 1/4, right? If the slope is 1/4, right? Essentially, what that means mathematically, tan theta is equal to the slope or the incline. So it means to get the angle of inclination, you can simply substitute 1/4 here because the slope is 1/4. Now, if they've given you the percentage of the slope, if they say it's 80%, essentially what they mean is that the slope, 80% is 80 over 100. If that's the case, we know tan theta is equal to the slope. If the slope is 80 over 100, it means to get the angle theta, it will be equal to, tan theta will be equal to tan. Tan theta will be equal to 80 over 100. And then from here, you then solve for your theta. That's how you look at it.
is that? Can you please explain the one at the top, the 1/4? What happened there? This the
So
one
I,
over four.
so I said, yeah, if the slope has been given as 1/4,
Okay,
if in the statements they say the slope is 1/4 or the gradient, right, of the slope is 1/4, right? Mathematically, tan theta is equal to the slope. So if the slope is equal to 1/4, it means tan theta is equal to 1/4. Similarly, if they say the slope is 80%, right, you again use the very same logic. that tan theta is equal to the slope. So if the slope is 80%, 80% is the same as 80 over 100, which means tan theta is equal to 80 over 100. And then from here, to get theta, it's arctan of 80 over 100. Are we clear?
Yes, I got it, sir.
All right. Anything else?
For now, I don't have, sir.
All right. Uh, then we can end things here. All right. Make
Thank
sure
you, sir.
you are done with dynamics at least by the end of this weekend, so we can start with hydraulics. No?
Yes, sir.
All right. Enjoy the rest of your weekend. Yeah.
Okay, thank you, sir.
Sharp.
Bye.